Okay, so in this problem, we have a person here, and they're a skier. This kind of looks like some funny skis. And they're going in this direction to the right. This person has 62 kilograms. That's this person's mass. They're going 6.5 meters per second. And this place here is frictionless, so nothing is slowing it down. This person's not accelerating, right? It's just moving at a constant 6.5 meters per second, right? So there are no forces left or right, because so nothing's pulling it, nothing's pushing it back. He's just chilling out, going along 6.5 meters per second. But then he runs into a rough patch right here, and this is 4.2 meters long. This patch right here, and the coefficient of kinetic friction is 0.3. So this is going to cause this person's velocity to go down. Maybe not zero, but it'll decrease. After the person gets past this little rough patch, it's then frictionless again, and then there's a downward slide. This is all frictionless, and then it evens out again, and once again frictionless. The question is, what's his speed? So his speed initially is 6.5 meters per second, but what's his speed at the bottom of the hill? Okay, and then it drops down 2.5 meters. So you can look at this from an energy perspective, right? You can say, okay, here's this person. What's this person's total mechanical energy? And mechanical means kinetic plus potential, okay? So we can say, draw like a line here and say, okay, he has some amount of kinetic energy. And, okay, I'll call this potential energy here. Well, actually, maybe I'll just put it inside. Yeah. This is his potential energy, and this is his kinetic energy initially, okay? So what's his potential energy? Well, it's mgh, right? It's mass. This is his mass. G, of course, is gravity. And then h is how high up is he? He's up 2.5 meters, okay? So mgh, mass times gravity times this displacement, 2.5 meters. You do all that, and you end up with 1519. 1519, of course, this is in joules, potential energy. Kinetic energy, that's 1/2 mv squared. So here he is. Kinetic energy is motion, right? So he's moving at 6.5 meters per second. So it's 1/2. That's half, obviously. M, that's his mass, 1/2 times 62. And v squared is 6.5 squared. 6.5 squared, you do all that. And you end up with 1309 joules. Okay? So that's what we have. And that doesn't change. So this total mechanical energy is fine. Nothing, no problem, no problem, no problem. And then once he runs into this, then that's friction. Friction is going to do negative work, right? So it's not going to add on to potential or kinetic energy. It's going to take it away. Now, what energy is it going to remove? Is it going to remove potential energy, or is it going to remove kinetic energy? Well, potential energy means how high up you are. So if you're going across this, is this changing your height? No. So the potential energy after going across this is not going to change your PE. But it is going to slow you down. And slowing you down lowers your velocity, which is going to lower your kinetic energy. So this is going to cause your kinetic energy to go down. Okay? But how much? So let's create a little free body diagram. So he's got mg going down. He's got this normal force going up. Mg is his mass, 62. Gravity, 9.8. So this ends up being 600 equals 607 newtons. And because the sum of the forces in y equals 0, because he's not accelerating up or down, that means mg has to equal n. Obviously, the signs are negative. So this is also 607 newtons as well too. And then the friction is in this direction, right? Because he's accelerating or not accelerating, but he's moving in this direction. So friction is opposite to the way he's moving. So the friction is this way. So it's kinetic friction, which is mu sub k times the normal force. Mu sub k, of course, is 0.3 The normal force is 607. You multiply those together and you get 182. So this is 182 newtons, right? And so if you did a force versus displacement graph, it's 182 newtons, right? So this is 182. And because it's moving parallel with the force is moving parallel with the object, you just multiply them together, okay? So this is the force, and the displacement was 4.2 meters. 4.2 meters. And if you remember, in the area under the curve is the actual work. So 182 newtons times 4.2 meters is 764 joules of work. So that's how much friction is taking away from kinetic energy. So you have this kinetic energy, and you're going to subtract, like, maybe this much of it, 764 joules. Okay, that's how much. Then this is friction. The energy due to friction. Okay, and then once you've done that, then you're on the other side. Then you're on the other side. Okay, so once again, this amount of energy is here. Then he goes across this. And now we've subtracted this frictional energy from the kinetic energy, right? But then what happens is, well, actually, if you do that, then you'll end up with like something that kind of looks like this. Something that kind of looks like this. So the potential energy is still the same. PE is still the same, 1519. That didn't change. But the kinetic energy is 1309 minus 764. Is equal to 545 joules, okay? But something happens. He now goes from here to here. So he now takes all his potential energy, and now his potential energy has been converted into completely kinetic energy because there's no friction here. Has been converted completely into kinetic energy. So finally, everything is now kinetic energy. So now this whole thing is now kinetic energy, right? We took 1519 plus 545, and you end up with 2064 joules, right? And then if you do 2064, which is in energy, is equal to 1/2 mv squared, multiply by 2, like that, get rid of that. Take your mass is 62, is 2, take the square root of that, and you'll end up with the V, or the velocity, 8.15 meters per second. So at the bottom of the hill, he has 8.15 meters per second. Okay, so let me just highlight some of these things. So this is your potential energy. This is also your potential energy. This here was your kinetic, right? This is all kinetic, and this is kinetic, and then I'll make this color here friction. Okay, so you can see that the energy is moving as this person here is moving this way and down. You can see the energies are changing, right? I have potential and kinetic, then I'm subtracting this frictional energy from this energy, and then then my mechanical energy is now smaller. I go down the hill, and now my potential energy is gone, and now all I have is kinetic. So you can see as this person is moving, work is happening, and this work is changing the energy in the system.